Hello and welcome back to the Ultimate VLSI and Embedded System course. In this course, we'll take a structure and practical approach to the three of the most powerful domains in modern electronics and computing: Internet of Things, VLSI design, and embedded system development. We'll start by building a strong foundation, helping you clearly understand how embedded system functions and how VLSI enables modern chip design. Then we'll move on to the IoT, where you will learn how these systems come together to create smart, connected technology. From basic principles to hands on skills, roadmaps, and real world applications, we have got it all covered. You'll also explore tools, career paths, and industry trends that are shaping 2025 and beyond. Whether you are an engineering student, a tech enthusiast, or someone looking at a smart, high impact career in electronics, this course is designed to equip you with everything you need to succeed. Let's get started. Before we begin, are you ready to elevate your expertise in IC design? IIT Bombay e-Postgraduate Diploma in IC design is your getaway to advanced knowledge and career transformation in semiconductor industry. Developed by IIT Bombay's Department of Electrical Engineering, this 12-month program blends academic excellence with real-world application. This live, online, and interactive course is delivered directly by IIT Bombay faculty and includes a prestigious campus immersion experience. You will earn 36 IIT Bombay Outreach Program credits, which can be saved in your academic bank of credits, and receive a diploma that grants you IIT Bombay alumni status. The program features core and elective courses in semiconductor devices, analog and digital design, mixed signal circuit, GAN mimics, and RFICs for wireless communication. You'll also gain access to IIT Bombay's lateral hiring group, connecting you with top-tier industry opportunities. With the access to design tools like Synopsys, 24 live sessions per course, expert tutorials, peer discussion via Slack, and support from a dedicated cohort manager, this program offers a truly immersive learning experience. Whether you're applying for yourself or nominating your team, the EPGD in IC Design from IIT Bombay is your next step towards technical excellence. Hurry up and enroll now. Find the course link in the description box and in the pinned comments.
Until recently, access to the internet was limited via devices like the desktop, tablet, or smartphone. But now, with the Internet of Things, aka IoT, practically all appliances can be connected to the internet and monitored remotely. It is a system of interconnected devices that transfer data over a wireless network without any human intervention. So hey everyone, welcome to this IoT tutorial video. In this video, we help you understand what IoT is and how it is impacting our day-to-day life. We will also understand the IoT architecture and look at the new trending IoT projects for 2021. But before that, if you haven't subscribed to our channel already, make sure to hit the subscribe button and the bell icon to never miss an update. I'm sure you're excited to learn, so let's dive right in.
Imagine you're at work and realize that you might not have turned off the air conditioner while leaving your house. Instead of traveling all the way back home, what if you could use your smartphone to know the status of your AC and perhaps even turn it off? Wouldn't that be amazing? Well, yes. And this can be achieved with the help of the Internet of Things. Until recently, access to the internet was limited via devices like the desktop, tablet, or smartphone. But now, with IoT, practically all appliances can be connected to the internet and monitored remotely. IoT is shaping the way we live our lives. It helps us get a better insight into the working of things around us. So, what exactly is the Internet of Things? IoT is a system of interrelated devices connected to the internet to transfer and receive data from one to the other. A smart home is the best example of IoT. Home appliances like the AC, doorbell, thermostats, smoke detectors, water heaters, and security alarms can be interconnected to share data with the user over a mobile application. The user can now get detailed insight into the working of the devices around him. Think about it. Until recently, the internet helped people connect and interact with each other. But now, inanimate objects or things have the ability to sense the surroundings, to interact and collaborate with one another. For example, in the morning when your alarm goes off, the IoT system can open the window blinds, turn on the coffee pot for you, and even turn on the water heater. Although all of this is fascinating, there's a lot that goes on in the background to ensure seamless functioning. From effective communication between devices to accurate processing of the data received, a lot of components are involved. In the context of IoT devices, hardware can be classified into general devices and sensing devices. The general devices are the main components of the data hub and information exchange. They are connected either by wired or wireless interfaces. Home appliances are a classic example of such devices. The sensing devices, on the other hand, include sensors and actuators. They measure the temperature, humidity, light intensity, and other parameters. These IoT devices are connected to the network with the help of gateways. These gateways, or processing nodes, process the information collected from the sensors and transfer it to the cloud. The cloud acts as both the storage and processing unit. Actions are performed on the collected data for further learning and inferences. Wired and wireless interfaces like Wi-Fi, Bluetooth, Zigbee, GSMs, and so on are used to provide connectivity. To ensure its ubiquity, applications need to support a diverse set of devices and communication protocols, from tiny sensors capable of sensing and reporting the desired factor, to powerful back-end servers that are utilized for data analysis and knowledge extraction. To help you understand its working, let's take a simple scenario. Let's suppose you want to water your garden every time the moisture level in the soil drops. Instead of doing it manually, you could automate it using IoT. The sensors and actuators installed gauge the soil for its moisture. This information is sent to the IoT gateway with the help of communication protocols like MQTT or HTTP. The gateway significantly aggregates data and feeds it to the cloud with the help of Wi-Fi LAN. Once the moisture level drops, the system is immediately triggered and the sprinklers are turned on. However, with the information stored in the cloud, a detailed analysis like the time of the day the sprinkler was turned on, the rate at which the moisture in the soil reduces, and so on, can be done, and the report could be sent over to you on your smartphone over an app. With the improved response, monitoring, and analytical capabilities, IoT is being adopted in almost all industries and domains, opening doors to endless applications. Today, IoT is being used extensively to lessen the burden on humans. To name a few, IoT is deployed for smart homes, wearables, watches and bracelets, smart cars, smart farming, smart retail, smart grids, smart city, and smart healthcare. With such a wide spectrum of applications, the future of IT looks more promising than ever before. In 2018, there were about 23 billion connected devices, which was more than double the world population. According to experts, there will be over 80 billion devices by 2025. IoT is a vision to connect all devices with the power of the internet, always learning and always growing. Now that you have a picture of what IoT is, here's a simple question for you. Which of the following technologies is not used as an interface for a network? 1. Wi-Fi. 2. Ethernet. 3. Zigbee. 4. VPN. Give it a thought and leave your answers in the comment section below. 3 lucky winners will receive Amazon gift vouchers. The integration of IoT with other technologies like cloud computing, machine learning, and artificial intelligence is paving the way for many new and exciting innovations. And that is the Internet of Things for you in short.
The first wave of the internet revolution came in with the growth of personal computers. And in the second wave, the internet came right onto our palms. That is, with the advent of mobile devices. And here we are living the third wave, where all electronic devices are almost already connected to the internet, or will be in the near future. Yes, the Internet of Things will bring about the next industrial revolution and will drastically transform the way we live and experience technology today. Quite possibly, the Internet of Things will be as disruptive as the Internet itself, particularly when combined with big data and predictive analytics. But what exactly is IoT? The concept behind IoT is about connecting just about everything to the Internet in real time, which directly improves our quality of life and experiences. For instance, how are you watching this video right now? On a PC, a mobile, or a tablet? Well, whichever device you're using, it's definitely connected to the internet, and that means you're already using an IoT device. Sensors are becoming the endpoints of IoT networks, Wondering what exactly a sensor is? These sensors collect an increasing amount of context-aware data and information such as location, images, weather conditions, and inject them into networks, actuators, and applications in real time. Big data, analytics, and predictions have become apparent synonymous, helping perform and execute tasks seamlessly with minimal to zero errors. Are you ready to admit a major breakthrough? Life in the present is great, but the future looks like it could be way more exciting. How, you may ask? Since there are billions of physical devices around the world that are now connected to the internet, collecting and sharing data in real time, terabytes of data are going to become petabytes, which represents 1,000 terabytes each. There is going to be a shift from wideband networks to narrowband networks for better range. And you'll also soon witness the communication system transcend from 4G to 5G wireless communications. IoT will definitely be the paradigm shift of effective multitasking with massive applications. Now, let's have a look at the future with IoT environment. Imagine you're driving your smart car to work and you're quite late. Don't you worry, because your car can now provide the shortest route with less congestion. Not only that, the integrated sensors in the car alerts you about mechanical assistance. You also have the access to automatic temperature control, and not to forget, in case you're tired or weary, the car becomes self-driven since it comes with an accident prevention system. As you're driving, you see the smart farms through your window. Farmers are happier thanks to IoT, which helps them with better yield and provided more efficiency than ever. You might wonder how. With the help of systems like autonomous self-driving tractors, adaptive irrigation systems, soil health monitoring, and animal welfare monitoring systems, this is possible. You also see smart factories which use IIoT, that is, Industrial Internet of Things. With the help of analytics and automation systems, IIoT helps in tracking goods in real time, inventory management, automated delivery system, and much more. Now you're returning home from office. Your car can park itself automatically. Your fingerprint, voice, or even your smartphone is enough to control all home appliances, from lights to television and your door to water taps too. Are you excited to experience this smart future which is not far away? Of course you should be. The applications of IoT will be seen in every industry across sectors, be it education, healthcare, manufacturing, automotive, you name it. IoT is definitely going to have a role to play in each one of them. Possibly the fourth wave will be the Internet of Everything, or IoE, which would encompass all physical things, processes, data, and people through wearables and surgically implanted sensors, unlike IoT, which focuses only on physical devices. Change is the only constant, and the world will never be the same with the growth of ubiquitous connectivity. And IoT is sure to change the way billions of people live their lives today.
The wide Internet of Things. As a learner, you should learn IoT, as it provides better scope for future data scientists, as well as provides for promising career opportunities. You can also build and manage your own IoT for your home. As a company executive, you should learn IoT, because it will help you measure everything in the business. You also get real-time metrics, actionable data, and better connectivity across industries. After completing this course, you should be able to explain the concept of Internet of Things comprehensively, describe hardware, software, and other connectivity building blocks of IoT, describe design considerations pertaining architecture, framework, and interoperability, explain the security considerations with IoT pertaining to vulnerabilities, explain Industry 4.0, Internet of Everything, and social IoT, and finally, describe IoT framework in enterprises.
In the context of IoT devices, hardware can be divided into two categories: general devices and sensing devices. The general devices do the embedded processing and connectivity for the platforms. They are connected either by wired network or wireless interfaces. They are the main component for data collection and information processing. The current home appliances are a classic example of such devices that are controlled by a sensor. These sensors help solve common problems. Apart from sensors, actuators are another important device in IoT that performs similar functions with different capabilities. They work as interface between sensors and machines and collect various information like humidity and light intensity. This information is computed using the edge layer, which typically sits between the cloud and the sensor. They are the layers that store the intermittent transfer of information. Finally, the back-end server of the cloud processes this information. Both the sensors and actuators are the chief components of IoT. The sensors measure temperature, humidity, light intensity, and other key parameters of home environment. The second most crucial aspect of IoT is device management platforms, or DMPs. The DMPs, as they are shortly called, are the platforms through which the assets interact with the software layer through network gateways. DMPs come with various functionalities, which include firmware upgrades, security patching, and reporting of metrics. They also help develop alert mechanism for industrial equipment with more open source OS like Arduino. Overall, it is an important aspect of the management of the device penetration. Connectivity blocks. Connectivity blocks collectively is considered as the backbone of an IoT setup. There are various connectivity layers like USB, CAN protocols, and Modbus. The next generation protocols of Wi-Fi are LoRa and Zigbee. They can interface with any application or modules, a small device embedded in an object. The entire landscape is called gateway architecture. The various ports are 232.485 from USB. They come with gateway architecture. The device interface is important for the data transfer and enables digital transformation with third-party applications and systems. Communication protocols and standards. Let us try to understand the various communication protocols available to set up an IoT. The first is the satellite. This enables a cell phone communication through an antenna situated within 10 to 15 miles. They have a stable and universal connection. The second is the protocol is the Wi-Fi, and is based on 5 GHz frequencies. It provides internet access within a certain range and are an affordable option. It has well-protected protocols. The third is the radio frequency. It is the easiest form of communication. A few examples are Zigbee and Z-Wave, which use low-power RF radio. It consumes low energy, which is very advantageous. It is relatively simple to configure. The fourth in this list is the RFID. It uses wireless electromagnetic fields to identify sensors and objects. The good thing about it is that it does not require power. The fifth is Bluetooth, which is useful for short-term and short-distance data exchange. It is present in every smartphone and has sensors. The final one is near-field communication, or NFC. It uses electromagnetic induction and loop antennas. It comes with encryption, has low-speed communication, and is used for short-range data exchange. Future of IoT connectivity. IoT connectivity is the future, the launch of new technologies like 5G. The 5G with low latency and higher throughput will increase the penetration of IoT. 5G cellular technology is supported by the network for virtualization, even for the common use case, such as for a tea vendor, real-time predictive analytics can be available. So, overall, the delivery time is reduced with IoT. 5G and IoT are embedded technologies. Both can be sliced and diced for predictive analytics and real-time business decisions. 5G will help devices connect through a network with high-speed bandwidth. IoT device architecture. There are 4 layers in the device architecture. The base layer consists of IoT devices. This includes all the components, like sensors, with the ability to sense, compute, and connect to other devices. Let's move on to the second layer, which is the IoT gateway or aggregation layer. This layer significantly aggregates data from various sensors. These 2 layers form the definition engine, and they set the rules for data aggregation. The next layer is based on cloud. It's called the processing engine, or event processing layer. It has numerous algorithms and data processing elements that are ultimately displayed on a dashboard. This layer basically processes the data obtained from the sensor layer. The last layer is called the application layer, or API management layer. It acts as an interface between third-party application and infrastructure. The entire landscape is supported by device managers and identity and access managers, which are useful for security of the architecture. Many individuals and organizations have contributed to create and set this standard. It covers the entire network and endpoint systems. It brings a structural approach with security controls in place. It provides a demarcation based on its uses for enterprise that build IoT products. This standard has 85 detailed recommendations and a structured approach that can fit into any IoT ecosystem. It has a flexible framework addressing the diversity of the technology aligned to the regulation. It also has risk modeling capabilities for any organization to choose from, including endpoint ecosystems. The standard is very flexible and comes with the inbuilt risk assessments for any organization to adapt. Overall, it is an interesting standard and easy to get trained at. IoT security, best practices. There are many best practices in IoT security. Let us look at some best practices pertaining to IoT hardware. First of all, the hardware should be tamper-proof. They should have undergone dynamic testing with specific data protection algorithms and should be updated on firmware and patches. The network components must be authentic with encryption, kernel controls, and division of networks into segments. Other security measures include privacy protection for sensitive information and other regulations like safe harbor statements. There are many value drivers to help the Internet of Everything. The key drivers are employee productivity, supply and logistics, customer experiences, innovation, and time to market. Asset utilization. All the factors are tightly linked to generate a new revenue gains for any enterprise. Time to market and innovation. This will help with the competitive index of the organization. It will help discover MVP to reduce the cost of building and bring improvement in customer experience. Asset utilization is the form of digital, physical, and even smart assets. The asset discovery is the requirement for the establishment of the IoT ecosystem. Supply chain is also a key value driver and assesses the requirement of Internet of Everything. In addition to the drivers, there are significant elements. The elements stand in 4 buckets. The first is data, which encapsulates sending and analyzing data. The second bucket is the people, who are always connected and have contextual subject mapping with the real-time world for decision-making. The third bucket is the things which link people to machine with endpoints, IP addresses, and sensors. The last bucket is machine to data, which talks to the business value and action iteration, essentially building simple models to achieve corporate results. Internet of Everything. Growth engine. The Internet of Everything comes with a growth engine for any organization. It includes people, who are the most valuable resources. The process of making the right effort for the things that includes the physical devices, other objects, and the data taken from sensors to make actionable insights for decision-making is important. People, process, things, and data are the growth engine elements that gives a company an edge in the digital transformation world. With data privacy and transparency mechanism, it is important for every organization to follow Internet ethics and compliance. IoT and fleet management. Let's discuss some use cases of IoT. The fleet management is a classic example of IoT in application. In this domain, IoT is mainly used to track vehicles from one point to another. Using IoT technology, the entire fleet can be monitored with the support of RFID chips embedded within every car in the fleet. The same RFID can also be used to track products such as consumer goods, electronics, and food items. You can get real-time information on the routes that the fleet takes. There are OBD devices that can be used to track vehicles' behavior and performance, including fuel consumption and mileage. This can reduce the total cost and provide greater return on investment. According to a recent study, the IoT market will increase to $8.28 billion by 2021. Sensors linked to artificial intelligence help the bankers track all the activities in the back end. The advancements of mobile phones and digital assistants, along with 5G connectivity, makes customer experience seamless. First and foremost, it is data. Data is the new oil. Financial institutions have structured and unstructured data of the customers. They can slice and dice the data for profiling, segmentation, product launches, and digital services enablement. The data can create a large economic drive and give rise to new business models like NFC banking, digital assistance banking, and social media banking. With this transformation, Internet of Things provides a competitive advantage to the banking, insurance, and financial services, while the end goal remains to help customers save money and give a bundle offer. Let's understand how IoT revolutionizes various industries. With the advent of the Internet of Things, there are many industries experiencing digital transformation, such as financial services, healthcare, manufacturing, communications, energy, retail, and transportation. IoT has initiated changes at all levels: user, infrastructure, and large-scale applications. Analytics with real-time dashboard and IoT support allows informed decision-making for businesses. This also means that IoT is introducing a new revenue model for enterprises around the world. Learning objectives. By the end of this lesson, you'll be able to explain the IoT architecture and frameworks, describe the IoT interoperability and its design considerations, and discuss industry-aligned use cases. IoT device architecture. There are 4 layers in the device architecture. The base layer consists of IoT devices. This includes all the components, like sensors, with the ability to sense, compute, and connect to other devices. Let's move on to the second layer, which is the IoT gateway or aggregation layer. This layer significantly aggregates data from various sensors. These 2 layers form the definition engine, and they set the rules for data aggregation. The next layer is based on cloud. It's called the processing engine or event processing layer. It has numerous algorithms and data processing elements that are ultimately displayed on a dashboard. This layer basically processes the data obtained from the sensor layer. The last layer is called the application layer or API management layer. It acts as an interface between third-party application and infrastructure. The entire landscape is supported by device managers and identity and access managers, which are useful for security of the architecture. IoT reference architecture. Next, let's learn about the various layers in the IoT reference architecture. Device layer. The device layer is the main component where there are various devices like sensors that are interconnected. Some examples are Bluetooth connected via mobile phone and Zigbee via Zigbee gateway. The other devices include the Raspberry Pi that's connected to the Ethernet via Wi-Fi. This is directly connected to the communication layers, which are part of the second layer. Communication layer. The communication layer, or gateway layer, has REST protocols and other application level protocols. Both the layers are tightly coupled and generate an enormous amount of data. Now, the bus layer, or aggregation layer, acts as a message broker. It forms a bridge between the data and the communication layer for the sensors. This is an important layer for 3 reasons. It supports an HTTP server and/or a MQTT broker. It aggregates and combines communications via gateway, and it bridges and transforms data between different protocols. The next layer is the event processing and analytics layer, which drives data and provides transformation to the data generated. It provides the ability to do event processing. The data is stored in the database. The client layer is used to create a web-based engine to interact with external APIs. This can be fed into the API management systems. This layer helps create a dashboard and provides a view of the analytics and event processing. This layer helps communicate with systems outside the network using machine-to-machine communication. So, we've seen the comprehensive IoT reference architecture with various components, rule engines, interfaces, and security systems embedded. Cross-functional architecture is possible using Device Manager that provides a single platform for remote management. The Device Manager communicates with devices through set protocols. Device management uses device management agents and is responsible for the remote management of software. The identity layer has the capabilities of cybersecurity, including policy control and OAuth 2-token insurance. Other capabilities include identity services, XACML, PDP, and directory of users, e.g., LDAP. IoT reference frameworks. There are a lot of frameworks for IoT setup, but the most common is the ISO 30141, and it provides commonly used vocabulary, reusable designs, and best practices for any developer to design an application. It also has many secure application standards that derive the maximum benefit for the organization and reduce the risks. IoT standardization and design considerations. There are a number of IoT standards, and these are evolving over time. Some of the key ones are M2M, that is a machine-to-machine service layer that can be embedded in hardware and software to connect devices. Contiki, which is an open-source operating system for low-cost, low-power IoT microcontrollers. LightOS, a Unix-like operating system for wireless sensor networks. Random Phase Multiple Access. This is a proprietary standard for connecting IoT objects. The last one is Sigfox, a proprietary low-power, low-throughput technology for IoT and M2M communications. IoT interoperability challenges. IoT maturity comes with several challenges, specifically pertaining to interoperability and interfacing. The reasons are coexistence of multifarious systems, devices, sensors, equipment, etc., that interchange location-time dependent information in varied data formats, languages, data models, constructs, data quality, and complex interrelationships. Multi-vision system designed by manufacturers over time for varied application domains, making formulation of global agreements and commonly accepted specifications very difficult. New things that get introduced and that support a new unanticipated structures and protocols. Existence of low-power devices, which need to exchange data over lossy networks, and may have minimal likelihood or accessibility for a power recharge in months or years. IoT design considerations. When you choose an IoT solution, you need to consider several factors, like its wireless capability, functionality, interoperability, secure storage, immediate boot capacity, device categorization, bandwidth, cryptographic control, and power management. The design considerations should be a mix of the estimated average of all these components and indexed to balance the user requirements. You also need to set up a dispute resolution mechanism in case of failure in the long run. IoT device architecture, network, and cloud. There are 4 stages of integrating the different IoT processes. Stage 1, network things, wireless sensors and actuators. Stage 2, sensor data aggregation systems and analog to digital data conversion. Stage 3, the appearance of edge IT systems. Stage 4, analysis, management, and storage of data. As these stages are evolving, the devices, the network, and the cloud application must be leveled equally in the ecosystem for better stability and security. The IoT architecture is a combination of things, devices, platform, and sensors with data. Stage 1 of an IoT architecture consists of networked things, typically wireless sensors and actuators. Stage 2 has internet gateways and data acquisition systems that includes sensor data aggregation systems and analog to digital conversion. In Stage 3, edge IT systems perform pre-processing of the data before it moves to the data center or cloud. Finally, in Stage 4, data center and cloud is where the data is analyzed, managed, and stored on traditional back-end data center systems. Fundamentally, we need to have a functional, scalable, available, and maintainable architecture. If these are not supported, then architecture is not useful. Now, let's look at the 3 architecture areas of IoT. 1. The client side, IoT device layer. 2. Operators on the server side, IoT gateway layer. And 3. A pathway for connecting clients and operators, IoT platform layer. These 3 layers interface with each other on the data synchronization front and pathway to generate more data from various applications. The feasibility of the layers depends on their application. Let us now differentiate between centralized and decentralized IoT architectures. The centralized architecture is a hub and is managed from one point, whereas the decentralized one is based on the use case. They do not help in the industrial IoT solution. The centralized architecture is associated with cloud architectures, in which a central hub provides a series of back-end services to smart devices. In decentralized architecture, there are many scenarios that require autonomous communication between smart devices in an IoT topology without the need of a central hub. The centralized systems help in event processing, and whereas decentralized systems operate more of peer-to-peer messaging. The decentralized auditing is one of the essential features in a decentralized architecture. Use case, IoT smart farming. Use case, smart farming, IoT design. This use case addresses the design formalities using IoT. IoT design is an essential part of the navigational ecosystem. Smart farming requires precise architecture and components that help bring benefits to the farmers. The various factors that determine the IoT design are data, cost, efficiency, and product quality. The efficiency and durability of the ecosystem help the farmers plan their harvest and sow based on the climatic conditions using the sensors and geospatial location data. So, to be precise, any farmer needs to understand the fundamental design that can help run the ecosystem. Smart farming is useful as it helps the farmer to predict conditions and sow crops with less cost and utilize the automation capabilities. To have such systems, you need to purchase the right hardware, which can monitor the accuracy of data and quality of the sensor. Once you have these systems, you can benefit more from farming. There are 4 things you need to integrate for smart farming. First is a data engine. Smart farming should have a robust data processing engine that can act as the brain and handle data processing, storage, and lead to efficient output. The second is hardware. You need to ensure that the hardware is durable and easy to maintain. Hardware with self-fixing algorithms is even better. The third aspect is mobile access. This is possible using a smartphone along with offline or online mobile applications. To enable all three processes, you need cloud infrastructure with the edge layer. This IoT system can enable smart farming for any crops in any geographical location. Let us look at another use case on using SIM cards to monitor sugar level in a diabetic patient. Diabetes management is a recurring concept where the patient has to check the blood sugar at regular intervals. In the traditional way, he has to go to the physician lab or he has to have his home blood glucose monitoring system. IoT can help create a system where the blood glucose data will be transmitted remotely via smartphone and a SIM embedded in it. Identifying the necessary and right hardware is one of the crucial steps of creating such a system. You need to choose the sensors for your device, or create a custom one which fits the glucometer. This can be a SIM card. The next step is to ensure that the quality of your sensors is good and has seamless integration with the system. Finally, make sure that the data monitoring happens in real time with high accuracy. Now, when the hardware landscape of this ecosystem is ready, you need to set the software then. First, it is crucial that you have software with self-repair algorithm for service management. To enable this process, you need cloud infrastructure with edge, and finally, a smartphone to work with the devices and sensors. Key takeaways. Now that you have completed this lesson, you should be able to explain the IoT reference architectures and frameworks, describe the IoT interoperability and its design considerations, and finally, discuss industry-aligned use cases.
Here's a list of IoT projects for 2020. First up is Smart Mirror. Smart mirrors are a very cool IoT application. These mirrors can be used to display temperature, news, weather, calendar, clock, and compliments on the screen. Apart from these, smart mirrors can be used to click the perfect selfies with a built-in camera. It can also be installed with speakers to play some music, and they also provide on-demand workout sessions with world-class trainers. The mirror can be used to browse the internet, make phone calls, and even be connected with other devices for collaboration. Next up is Smart Money Transfer. We're heading towards complete digitization. Transactions are made possible on your cell phone with apps like Apple Pay, Google Pay, and PayPal. But imagine if you could walk to a store and pay with a wristwatch. Wouldn't that be cool? The purpose of the smart wallet is to provide an easy and reliable platform for money transactions. It is compact, wearable, and rechargeable. For safety purposes, the user authenticity is validated. The smart money transfer technology can reduce the burden of mobile money transfer. When you're on the go, you could easily step into a store, purchase the goods, and pay hassle-free. After every successful transaction, the balance is updated immediately to avoid any uncertainty. Next up is IoT-based Smart Arm. Now this project includes the creation of a robotic arm which can pick and place things from one place to another. To control this action, the robotic arm can be moved using specific commands. Some advanced arms allow the user to change the end effect of the arm to perform various different actions. It can be used to make art, print 3D images, and build production lines. It can also be used to perform your day-to-day chores. At number 4, we have Smart Irrigation. Now, with change in climate and recurrent water crisis, farmers suffer a great deal with growing crops. Smart irrigation puts an end to this ordeal. This system comes with a moisture sensor that checks the soil for its water content. When the soil moisture drops below a certain value, the system triggers the water supply. At number 5, we have Smart Door. Now, as the name suggests, this project aims at creating smart doors that control the entry and exit of humans. These doors open and close automatically when you pass by. The door can also be controlled remotely. You could unlock the door for a friend by tapping an icon on your smartphone. Once they exit, you're immediately notified. The owner can also choose who has the access to the door. At number 6, we have air monitoring system. Now, air monitoring has become crucial for the environment, and what better way to do it than incorporating IoT. The IoT system uses air sensors to sense the presence of harmful gases or compounds in the air. The data collected can be used by the local authorities to make a detailed analysis. Necessary actions can also be taken to ensure that the air quality levels don't reach an extreme low, especially in areas with hospitals and schools. Moving on to number 7, we have smart alarm clock. Now, there are many variations of a smart alarm clock, but the alarm we are talking about is a self-setting alarm. This smart alarm clock uses your Google Calendar to check your appointments to set the alarm. It can also procure data from GPS about your ETA to a particular place and consider the weather to automatically adjust your wake time. All of this is just making life more easier. Moving on, at number 8, we have IoT-based weather reporting system. Now, the system deals with monitoring weather and climate changes like humidity, temperature, moisture, wind speed, UV radiation, light intensity, and even carbon monoxide levels in the air using multiple sensors. Now, these installed sensors send data to the web page that is plotted as graphical statistics. The project even consists of an application that sends notifications as an effective alert to warn people about sudden and drastic weather changes. So when you're heading out, the app could easily tell you what the weather will be like and suggest carrying an umbrella or perhaps a sunblock. At number 9, we have smart wheelchair. There are over 132 million wheelchair users across the globe. Smart wheelchairs is an excellent innovation. Typically, it comes with built-in sensors on the seats that collect data every second. The data provides insight into the seating behavior of the patient and the energy required to maintain the posture. Other variations of smart wheelchairs could include fall detection. These features allow people to monitor the patient from a remote location. And finally, at number 10, we have smart street light system. This IoT-based street light monitoring system not only monitors but also ensures low power consumption and detects faulty lights. The street lights have external sensing that automatically turns on at the desired intensity based on the lighting needed. Control of light intensity is based on the movement of people or vehicles. In case of an emergency, the lights increase their brightness to maximum intensity, thereby ensuring safety. When deployed as a part of a smart city, the users can be informed about any outages. They can also register a complaint for immediate service.
One of the most common mistakes many aspiring engineers make is trying to absorb every piece of content labeled as VLSI or semiconductor on LinkedIn or YouTube. But in today's landscape, especially after 2024, hiring practices have changed significantly. As a result, preparation strategies must also evolve. To make this process clear, today we have come up with our video on VLSI Career Roadmap. This video is divided into 3 segments. First, we are going to discuss how hiring has changed and why the approach must be different now. Next, we are going to discuss about the core topics that every candidate must master, regardless of domain. And finally, we are going to cover domain-specific preparation, covering exactly what to study for RTL design, verification, physical design, and DFT. So guys, if you want to learn more about it, watch this video till the end. Now first, let us discuss how hiring has changed since 2024. Earlier, semiconductor companies typically conducted general hiring drives. A central recruitment team assessed fresh graduates on broad fundamentals like digital design, analog basics, signals, and so on. Successful candidates were then randomly allocated to available openings in the RTL, verification, physical design, or DFT department. Today, this model has shifted. Hiring has become domain-specific. If the verification team needs people, then that team interviews and evaluates the candidates by itself. Even if the process starts with general topics, the discussion quickly dives into domain-specific knowledge. This means candidates are assessed not on just fundamentals, but also whether they are ready to contribute to a particular role or not. So guys, you would have got a brief idea that what our employers are looking for. Studying only generic concept is no longer enough. A clear focus should be there on both fundamentals and specializations. Now, let's move ahead and try to understand what are the core topics you must master before anything else. Before you even think about diving into any domain-specific preparation, there are important foundational topics that you must get comfortable with. Let's go through them together. First up, we have digital electronics. This is the backbone of everything you will design. So whether you are in front-end, back-end or verification, this is very much important. Make sure you thoroughly understand topics like combinational and sequential logics, flip-flops, multiplexers, and finite state machines. If you're wondering where you can start with, for reference, Digital Design by Maurice Mano is still one of the best books out there. You can start from there. Next up, we have Verilog. Verilog is that what translates your idea into real hardware. Learn not only the syntax, but also how your code actually maps up onto gates and flip-flops in silicons. This is also one of the very most important topics. On the third priority, we have CMOS. Even if you are more interested in design or verification, you still need to understand what happens at the transistor level. So focus especially on NMOS and PMOS work and why CMOS inverters are so fundamental. Next up, we have computer architecture. Ask yourself, do you really know how a processor fetches, decodes, and executes instructions? This isn't just academic, but it helps you write better code and debug real hardware issues. Next up, we have static timing analysis or STA. This is where actually a lot of candidates struggles. So don't try to memorize formulas blindly. Understand concepts like setup and hold time, clock skew, jitter, and uncertainty. Once you feel confident, jump straight into solving problems, timing questions that always come up in the interviews. Now, at the sixth point, we have C programming. Yes, the same language which we generally study in our college days. Something coding isn't needed in VLSI, but that's a misconception. Whether you are using EDA tools or automatic flows, C helps you think logically and solve problems effectively. Seventh one, we have ASIC design flow. Take time to see whole picture. Know what happens at every stage from RTL coding, synthesis, flow planning to tape out. Understand this flow helps you see where your work fits into bigger process. So you need to have a better understanding of ASIC design flow. At 8th, we have lower power design techniques. So guys, I'll tell you a very interesting fact. In today's scenario, chips have shrunk to 3 nanometer nodes, and that makes power management more critical than ever. So you will have to learn how leakage, dynamic power, and static power affect your design and what techniques help to reduce them. So this is one of the very important concepts and you need to master that. Now, candidates who have strong fundamental in these areas consistently outperform those who just skim topics superficially. So guys, be patient, master the topic first, and once you have this foundation, dive into domain-specific preparation, which we are going to discuss right now. So once you have built a strong foundation in the core topics we have covered earlier, it's time to start thinking about where you want to specialize. Broadly, you will choose between front-end roles and the back-end roles. Let's break it down one by one. For the front-end role, like if you are more interested in coding hardware, verifying designs, or making circuit testable, you'll likely gravitate towards front-end role like RTL design, verification, or DFT. Let us discuss each one of them one by one. RTL stands for Register Transfer Level. This design is all about translating functional code into synthesizable code. Here's what you need to focus on: Verilog and System Verilog mastery. Learn to write clean, efficient RTL code that synthesizes correctly. Then in this, you will also have to understand digital design and STA. You must be confident with timing constant, setup, hold checks, and how they impact your design. Next, you need to understand how to handle metastability and synchronizing data across different clock domains. Next, we had discussed about the importance of C programming and scripting, which will strengthen your logic and algorithm skills. And also, Python or Perl can help automate repetitive tasks. For hands-on tools, start practicing with EDA Playground, simulate designs, write constraint, and synthesize your modules. Next up, we have verification. Verification ensures that design works exactly as intended. If you enjoy testing and debugging, this might be your domain. Now, the key areas that it covers is System Verilog and UVM, where you need to master System Verilog for test bench development, learn the universal verification methodology to build reusable environments. Then you need to have an idea about OOP concepts, then about protocols like AXI, AMBA, AHB, and also you need to develop debugging skills. Learn to trace simulation failures and identify the root causes. Now, next up we have in the front-end role, DFT, Design for Testability. It focuses on making chips testable once they are manufactured, so defects can be identified early. Now in this, you need to master testability and ATPG, learn about automatic test, pattern generation, and how scan chains are inserted into designs. Next, understand about stuck-at faults, transition faults, and how they are detected. And finally, understand about clock domain crossing. It is also very much important. Now, let us discuss about the backend role. If you are drawn to physical implementation, timing closure, and getting a design ready for fabrication, you will want to focus on backend roles. Backend covers synthesis, physical design, physical verification. Now, the core areas to focus on are deep CMOS understanding, advanced STA and clock tree synthesis, and floor planning and placement. Let us try to understand each of this one by one. So, for CMOS, you need to learn how transistors behave at the physical level, like leakage currents, power consumption, logical effort, all that thing which impact performance. Next up, you need to understand how device sizing influences speed, area, and power trade-off. And finally, study about short channel effects and their impact on scaling and device reliability. So, for backend, this is the very important concept if you want to go in CMOS. Next up, we have advanced STA and CTS. Go beyond the basics. You need to be comfortable with clock skew, multi-cycle paths, and false path. Then you have CTS, which is clock tree synthesis. And this is the favorite topic asked in the interviews. You must be clear on how clocks are distributed, balanced, and optimized for minimal skew and latency. Finally, we have floor planning and placement. Know how to place macros, design a power grid, and avoid congestions in layout. So this is also very much important, guys. Now, these things are covered only when you have a solid foundation on the fundamentals that were discussed in the earlier slides. Now, as a beginner, you would be wondering which path to choose. Think about what excites you the most. Do you prefer coding, simulation, and verifying behavior? Front end may suit you the best. Or do you like enjoying optimizing layouts, working with physical constraints, understanding how designs come to life on silicon? Then backend is your calling. So first, make your fundamentals very strong, then go into the domain specific. Prefer the type, like which one you want to choose, because we have discussed about what role you'll be playing either in the front end or the back end side. And guys, one more important note, that you need to have amazing projects on your portfolio. Projects are not optional. They are the first thing that recruiters will look at your resume. So don't leave it at all.
Hello everyone and welcome to this course on VLSI Design. So in this course, we will dive into the world of very large scale integration, which is also known as VLSI, a key technology that powers modern electronics. Whether you are a beginner or looking to refresh your knowledge, this course will provide you with a comprehensive understanding of VLSI design and its practical application in real world devices. So first, we will introduce the fundamentals of concepts of VLSI technology. We will discuss what VLSI is and how chips are made, including the basics of fabrication. You will also learn about transistor, the building blocks of VLSI circuits, and the foundational NOT gate that drives logic operation. In Module 2, Building Circuits, we will explore the process of designing circuits within a VLSI framework. We will cover logic circuits for mathematical operation as well as sequential circuits that handle memory. Additionally, you will learn about clocking, which is crucial for coordinating the operations within the chip. In the third module, we will teach you how to describe VLSI designing using hardware description languages like Verilog. You will also learn how designs are tested virtually through simulations and how quick prototyping with FPGAs helps in validating designs before fabrication. In Module 4, the final module will take you through the process of turning VLSI designs into physical chips. We'll cover the physical design arrangement, the importance of chip testing for the quality assurance, and the tools used by engineers to facilitate these tasks. So by the end of this course, you guys will have a solid foundation in VLSI design and be well prepared to explore more advanced topics in integrated circuit design. So basics of VLSI. So very large scale integration, VLSI is the process of creating integrated circuits, ICs, by combining thousands, millions, or even billions of transistors into a single chip. VLSI technology has changed the world of electronics by enabling the development of complex and powerful devices like computers, smartphones, and more, all while reducing the size and power consumption of these systems. Before the advent of VLSI, the integration of electronic components on a chip was limited to just few transistors. However, as technology advanced, it became possible to integrate a massive number of components into a single chip, making circuit faster, more efficient, and more affordable. So in this module, we will explore the basics of VLSI, how chips are made, the roles of transistor as electronic switches, and how the NOT gate serves as the first building blocks in digital logic. So what VLSI is? VLSI stands for Very Large Scale Integration, which refers to the process of integrating a large number of electronic components, primarily transistors, onto a single chip. So these components can include not just transistors, but also diodes, resistors, capacitors, and other essential components needed for an integrated circuit, which is also known as ICs. So the number of components integrated onto the chip has been steadily increasing over the decades, from a few hundred components in early chips to billions of transistors on modern processors. VLSI enables the creation of complex circuits, including microprocessors, memory chips, and other digital circuits. It also allows for the miniaturizations for electronic devices, leading to the compact designs of modern-day electronic gadgets. In fact, modern processors include those used in smartphones and computers, contain billions of transistors in a space smaller than the fingernail. So the development of VLSI technology has had a profound impact on many industries, including computing, telecommunications, automotive, medical devices, and consumer electronics. So the driving force behind VLSI is Moore's law, which says that the number of transistors on a chip would double approximately every 2 years, leading to exponential growth in processing power and reduction in the cost. So now let's see how chips are made, the basic fabrication process. So the fabrication of VLSI chip is highly complex and delicate process that requires advanced technology, precision equipments, and clean room conditions. So it involves multiple steps, each contributing the creation of an integrating circuit that can perform its desired function. So the basic fabrication process consists some following steps, which are: the first one is the design and the planning. So before any physical work is done, the design of the integrated circuit is created. Engineers use specialized software tools to design the chip's architecture, ensuring that the arrangement of transistors and the other components will perform the required tasks. This is crucial stage in chip fabrication, as the design directly impacts the chip's performance, power consumption, and overall functionality. The second one is wafer preparation. So the fabrication process begins with a thin slice of silicon known as wafer, which serves as the base material for the chip. Silicon is chosen because of its excellent semiconductor properties, which allows it to control electrical currents efficiently. So the wafer is carefully cleaned to remove any contaminants that could affect the chip's performance. The third one is photolithography. So once the wafer is prepared, the next step is photolithography, which is used to transfer the chip's design onto the silicon wafer. A layer of light sensitive material called photoresist is applied to the wafer. So the wafer is then exposed to ultraviolet UV light through a mask that has the circuit design. So the areas exposed to light undergo on a chemical chain, allowing the pattern to be developed on the wafer. The fourth one is etching. So after the photolithography step, the wafer undergoes an etching process to remove unwanted proportions or portions of the photoresist and underlying materials. So etching can be done using various techniques, including dry etching using plasma and wet etching using chemicals. The remaining material forms the transistor gates and other components of the ICs. The fifth one is doping. So in this step, the wafer is exposed to different chemicals dopants to alter the electrical properties of the silicon in specific areas. Introducing dopants such as boron or phosphorus makes the semiconductor material either conductive N-type or less conductive P-type. So this creates the region in the silicon where transistors will be formed. Then comes deposition. So the wafer may also undergo deposition, a process in which thin layers of materials such as metals or insulators are deposited onto the wafer. So these layers are used to form various components, including the interconnections between transistor metal contacts and insulation between the different layers. Then comes metallization and packaging. After the various layers are created, the wafer is subjected to a metallization process in which metal, usually aluminum or copper, is deposited to create electrical connections between transistors. So finally, the wafer is diced into individual chips which are packaged to be used in electronic devices. So now let's jump into the transistor, the electronic switch. So one of the most fundamental components in VLSI technology is the transistor. So a transistor is the semiconductor device used to amplify or switch electronic signals and electrical power. So it is essentially an electronic switch that controls the flow of electricity between two terminals. Transistors are at the heart of every digital circuits and are used to build the logic gates that forms the basis of all computational process. So their transistors are made materials like silicon, which have properties that make them ideal for controlling electrical currents. A transistor typically has three layers: emitter, base, and the collector. So the base controls the current flowing between the emitter and the collector, making the transistor either conductive or non-conductive, depending on the signal received. In VLSI technology, field effect transistors (FETs) are the most commonly used type. FETs are used because they are more efficient and easier to miniaturize than the other types of transistor. So the metal oxide semiconductor field effect transistor (MOS) FET is the dominant type used in VLSI circuits. Transistors can be used in digital logic circuits to perform operations like switching, amplifications, and signal processing. So these operations form the foundation of modern electronic devices, as transistors control the flow of binary data, zeros and ones, in the form of voltage levels. So now let's move forward and see the first building block, the NOT gate. We will learn about gates in next module as well, but let's start with the NOT gate. So the NOT gate, also known as inverter, is one of the simplest yet most important components in digital logic design. A NOT gate takes a single binary input and produces the output opposite, or you can see produces the opposite output. So if the input is 1, which is true, the output is 0, which is false. And if the input is 0, which is false, then the output is 1, which is true. So the NOT gate is the most basic building block in Boolean algebra and digital circuits, and it is used in many more complex gates and circuits. In VLSI circuits, the NOT gate is implemented using transistors, and it plays a crucial role in performing logic operations that enables the functionality of microprocessors and memory units. Boolean representation of the NOT gate, which is this. Okay, if the input is 0, then the output will come 1, then if input is 1, then the output is 0. 0 means false and 1 means true. NOT gate in VLSI circuits. In VLSI circuits, a NOT gate is created using MOSFETs. The input voltage of the MOSFETs determines whether the transistors conducts or not. If the input is high, which is 1, one transistor is switched on, pulling the output low, 0. Conversely, if the input is low, 0, then the other transistor is switched on, pulling the output high, which is 1. So NOT gates are used in combination with the other basic logic gates such as AND, OR, and XOR gates, which we will learn in the next module, which will create more complex operations like additions, multiplications, and decision making in digital system. So in conclusion of module 1, the VLSI technology is the backbone of modern electronics, enabling the development of powerful, impact, and energy efficient devices. So in this module, we have explored the basics of VLSI, how chips are made, and the role of transistors as electronic switches, and how the NOT gate serves as the foundational building block in digital circuit. So the fabrication of VLSI chips involves intricate process like photolithography, doping, etching, and deposition. So transistors, specifically MOSFETs, are the heart of VLSI circuits, enabling the switching and amplifications of signal. So the NOT gate, one of the simplest logic gate, is built using transistor and serves as the first step in the construction of more complex digital circuits. So as technology continues to advance, VLSI will play an even more significant role in the development of future electronic devices, driving progress in fields such as artificial intelligence, quantum computing, and beyond. So understanding the fundamentals of VLSI will provide you with the foundation needed to dive deeper into the world of semiconductor design and digital electronics. So in the next module, we will learn about circuits. So in the world of VLSI design, building circuits is a critical skill. Circuits form the backbone of digital electronics, ranging from the simple logic gates to complex microprocessors. So these circuits are created using a variety of components that perform a specific task. They can be broadly classified into two types: combinational circuits and sequential circuits. Both play a crucial role in a digital system, but they function differently. Combinational circuits, such as those used in mathematical operations and the logical design, in contrast of sequential circuits, involve memory elements that store information about the state of the system and use in the historical data to make decisions. So the circuits built using two types of logics are the building blocks of all digital systems. In addition to combinational and sequential logic, the concept of clocking is essential to the operation of many digital circuits, as it helps synchronize various processors within a chip. So in this module, we will explore the basics of building circuits, starting with the logic used for mathematics and decision making, which is combinational circuits, followed by the logic for memory and state dependent operation, which are sequential circuits, and finishing with the clocking, the rhythm that keeps everything in the sync. So what are combinational circuits? Combinational circuits are circuits whose output is a direct function of their current inputs. In other words, the output is determined solely by the current input values and it does not depend on any previous inputs or states. So these circuits do not have memory and cannot retain any information about the past events. Combinational circuits are fundamentals for performing logical operations and mathematical calculations. So they are the building blocks for more complex operations and are the foundation for the arithmetic logic units ALUs in the processors, which performs calculation and decision making tasks. Let's jump to the basic logic gates. So combinational circuits are typically built using basic logic gates or logic gates, which are the fundamental building blocks of digital electronics. So these gates perform basic operations on binary input, zeros and ones, and produce a single binary output. So each gate has a specified logical function based on the Boolean algebra. So the most common logic gates include, the first one is AND gate. An AND gate outputs 1 true only when all its input are 1. It mimics the logical AND operations, meaning all conditions must be true for the results to be true. If any output is 0, the output is 0. Here you can see the graph, the truth table. If the input is 0, then output will be 0 because it's AND, A and B input. If input A is 0, input B is 0, again 0. If input A is 1, input B is 0, again 0, false. 0 means false, 1 means true. If the both input are true, then the output is true. Here it is written AND gate outputs 1 true only when all its input are 1. Here you can see the fourth line. All inputs are 1. Then the output is 1. Otherwise, it's 0. Then the second gate is OR gate. An OR gate output 1 if at least one of the input is 1. It performs the logical OR operation, representing a condition where only one or more input must be true for the output to be true. Here you can see if the input A is 0, input B is 0, then the output is 0. But if at least, here you can see an OR gate outputs 1 if at least one of the input is 1. Here you can see input A is 0, input B is 1, then the output is 1. Okay, so at least one input should be 1. Okay, 1 means true and 0 means false, then the output will be true. So this is the OR gate. Now let's jump into the next gate, which is NOT gate. So a NOT gate, also called an inverter, has only one input and outputs the opposite value. If the input is 0, then the output is 1, and vice versa. Here you can see if the input is 0, then the output is 1. If input is 1, then output is 0. Because it has only one input, here written, has only one input and the output the opposite value. So this is the NOT gate. Next gate is NAND gate. So a NAND gate is the inverse of the AND gate. If the output is 0, only when all inputs are 1. For all other input combination, it outputs 1. NAND gates are universal, meaning they can be combined to form any other logic gates. Here you can see if input A is 0, input B is 0, then the output is 1, because it is the inverse of the AND gate. Okay, the both input are true, then the output will be false. Fifth gate is XOR gate. And XOR gate, exclusive OR gate, outputs 1 only when the inputs are different. It is commonly used in arithmetic and comparison operation. If both inputs are the same, the output is 0. Here you can see if the both input are same, then the output will be 0. Here both inputs are same, 1 1, then the output 0. If both inputs are different, then the output will be 1, which is true. So these basic gates can be interconnected in countless combinations to create more complex combinational circuits for performing arithmetic operations, decision making, and data processing in computers and digital devices. So now let's move forward and see mathematical operations in combinational circuits. So combinational circuits can be used to perform arithmetic operations such as addition, subtractions, multiplications, and division. So a common example is the adder circuit, which is performed additional on binary numbers. So half adder is there. So the half adder is the simplest combinational circuit for adding two single bit binary number. It consists of an XOR gate to add the two bits and AND gate to generate the carry bit. Then there is another adder is known as full adder. So the full adder is an extension of the half adder. It adds two single bit binary numbers and a carry bit from the previous operations. It uses XOR gates for the sum and AND or OR gates to handle the carry bit. So by combining these basic circuits, we can create more advanced circuits such as multiplexers, encoders, decoders, and the ALUs, arithmetic logical units, all fundamental in digital system. So after understanding the combinational circuits, let's jump into the sequential circuits. So what are the sequential circuits? Sequential circuits are the circuit whose output depends not only on the current input values but also on the history of the inputs. So this means that sequential circuits have memory elements that allow them to store information about previous input. So these circuits can remember their previous states and use this information to influence future output. So the most fundamental type of memory element in sequential circuits is called flip-flop, which can be stored a single bit of data. Sequential circuits are used for tasks such as counting, data storage, and state machines, which are the critical in processors, memory devices, and other digital systems. So what are the flip-flops and the registers? A flip-flop is a digital device, meaning it has two stable states. It can store a bit of information, either 0 or 1. So the state of the flip-flop is controlled by clock pulses, which allow it to change its state at specific times. So flip-flops are used to build more complex memory elements like registers, which can also store multiple bits of data. So there are different types of flip-flops, like SR flip-flop. The SR is set reset. Flip-flop has two input. One is set and another is reset. And D flip-flop. The D means data flip-flop. Captures the value of input on the rising edge of the clock signal. The input data is transferred to the output when the clock pulse is received. Then comes JK flip-flop. The JK flip-flop is a more versatile flip-flop that can toggle its state, set or reset depending on its inputs. Then comes T flip-flop. The toggle flip-flop changes its state on every clock pulses, making it ideal for creating counters. So these flip-flops form the basic memory units in sequential circuits, and multiple flip-flops can be combined to create registers and memory blocks. Now let's understand what is clocking. So in the digital circuits, clocking is the process which all operations in a chip are synchronized. A clock is a periodic signal that provides timing for all the operations inside the circuit. Without a clock, it would be difficult to coordinate the operations of the millions or billions of components on a chip. The clock signals in a square wave alternating between a high 1 and the low 0 state at a regular frequency. So the frequency of the clock signal determines the speed at which operations within the chip occur, and it is measured in hertz. For example, 1 gigahertz clock signal oscillates 1 billion times per second. So what are the clocking in sequential circuits? So in sequential circuits, the clock signal is used to control the state changes of memory elements such as flip-flops. So the flip-flop only change the state on the rising or falling edge of the clock signal, which allow them to store information at a specific time. So the clock also synchronizes the operations other components in the system. For example, in a processor, the clock coordinates the fetching of instructions, the executions of arithmetic operations, and the storage of results. The speed of the clock determines how fast the processor can execute instructions, and modern processors can operate at clock speeds of several gigahertz, meaning they can perform billions of operations per second. What is clock domains? In clock systems, different parts of a chip may operate at different clock speeds. They are referred to as the clock domains, and managing the synchronization between them is a key challenge in chip design. Special techniques like clock domain crossing and synchronizations are used to ensure that the data is transferred reliably between different clock domains. So in conclusion of this module, we explored the essential concepts of building circuits, focusing on combinational circuits, sequential circuits, and clocking. So combinational circuits made from the basic logic gates are used for mathematical operations and decision-making tasks, while sequential circuits include memory elements like flip-flop that allow circuits to store and use past data that synchronize all operations within a chip, ensuring that the processor occur in a coordinated and timely manner. So these concepts form the foundations for designing digital systems, from simple circuits to complex microprocessors, and they are crucial for anyone interested in understanding how modern electronics work. As we continue to design faster, more efficient systems, the ability to build and understand these fundamental circuits will remain essentials in VLSI design. So in the next module, we will learn about VLSI designs and the Verilog part. So in the field of VLSI, very large scale integration design, engineers face the challenge of creating highly complex, efficient and reliable integrated circuits, ICs. So the development of these ICs require both precise design methodologies and tools that allow for accurate descriptions, simulations and verification. So this module will explore three key concepts or aspects of VLSI design. The first one is describing chips and the Verilog part, testing designs virtually simulations part, and quick prototyping with FPGAs. So each of these topics is integral of the process of developing, testing and finalizing the VLSI design. So let's start with the what is Verilog. So Verilog is a hardware descriptions language, HDL, used to model and describe the behavior and structure of electronic system. It is one of the most widely used language for describing digital circuits and systems at different levels of abstraction, including the gate level, data flow level, and the behavioral level. So with Verilog, designers can write code that specifies the operation of a digital system, such as microprocessors, memory, or any other VLSI component. So Verilog allows designers to describe the functionality and timing behavior of digital circuits, enabling them to model how circuits will behave over the time and under different conditions. So this is very crucial in the VLSI design process, as it allows engineers to conceptualize and validate complex design before actual hardware implementation. Now let's jump into the levels of abstractions in Verilog. So there are the different levels. So the first one is the behavioral level. So in this level, Verilog code is written to describe the functionality of the circuit without worrying about its detailed structure or the specific component used. So the designer specifies what the circuit should do, how it should do. For example, a designer might write code to describe how a circuit adds two numbers together without specifying the gates or register used. Fine. The second level is data flow level. At this level, the designer specifies the flow of data through the circuit, typically using continuous assignment and operation. So the focus here is still on the data movement and repeat and the logic of the circuit, but it begins to introduce some structure details such as the use of specific logic gates and or another gate. Third one is structural level. So this level involves the most detailed descriptions of the circuit, specifying exactly how different components are connected. This level of abstraction uses modules that represent actual hardware elements such as gates, flip-flops, and other fundamental components, and show how these components are integrated. Then comes the gate level, the last level. So gate level description focuses on the actual gates used in the circuits and how inputs and outputs are connected. Verilog can be used to define a circuit entirely in terms of logic gates, creating an accurate low-level representation of the design. So after understanding the levels in the Verilog, let's understand what is simulations in VLSI design. So simulation is the process of testing digital design virtually using specialized software tools before implementing it in a hardware. Simulation allows designers to verify the correctness of their designs, check for the potential issues like timing, violations, and ensure the system behaves expected. Since VLSI design can be highly complex and contain millions of transistors, it is not practical to test them physically at every stage of the design process. Instead, simulations allow engineers to simulate the behavior of their design in a controlled virtual environment. So now let's understand now types of simulation in VLSI. So the first one is functional simulation. Functional simulation is a type of simulation checks where the design functions correctly. That is, whether the logic described in the Verilog code produces the expected result. Functional simulation does not take into account timing issues. It simply verifies the logic of the design. It is typically the first step in the simulation process, as it helps catch basic errors in the design before the complex timing issues are considered. The second one is timing simulation. Timing simulations takes into the account delays associated with the circuit, such as propagation delays and setup hold time valuations. So this type of simulation is crucial in ensuring that the designs will work correctly at the speed the designers expect. Timing simulations are particularly important for the high-speed circuits like processors, where even small things errors can cause the design to fail. The third point is gate level simulation. So gate level simulations simulates the design at the lower level, typically using a netlist of logic gates. This type of simulation is used after a design has been synthesized, and it is helpful in verifying that the gate level implementation works as needed. The last type is post-synthesis simulation. After the design has been synthesized into a netlist, post-synthesis simulation is used to verify that the synthesized design matches the original specification and meets timing constraint. So this stage is critical in ensuring that the final design will be manufacturable. So now let's see some simulation tools. So there are several industry standard tools available for simulation in VLSI design. So here are the few. The first one is Model Sim, Advanced Simulation and Debugging. So Model Sim is one of the most widely used simulation tools for VLSI design. It supports both functional and timing simulation and can handle large designs. Model Sim is often used in combination with other tools like Cadence or Synopsys. Then the second is Vivado. Vivado is an integrated development environment IDE from Xilinx used for designing and testing FPGA-based systems. It includes simulation tools for both Verilog and VSDL designs and can be used to simulate both logic and timing. The third is Cadence. Cadence is another powerful simulation tool that supports both Verilog and VSDL. It is used very large scale design and can simulate everything from basic functional verification to complex system level validation. Now you will be wondering, what is the importance of simulation? So simulation is a critical step in VLSI design because it allows engineers to catch errors in early stage in the design process, reducing the risk of costly mistakes during fabrication. So virtual testing ensures that the design works as intended and meets the required specification before it is physically manufactured. Fine. So now after understanding the simulation part, so now let's understand what are FPGAs and how FPGAs are used in VLSI prototyping. So FPGAs are widely used for quick prototyping in VLSI design because they allow designers to implement and test their design before committing to the expensive and time-consuming process of manufacturing an ASIC, application-specific integrated circuit. With an FPGA, a designer can implement the Verilog descriptions of a chip and test it in hardware, allowing for early detections of issues that may not have been apparent in simulation. So what are the advantages of FPGAs for prototyping? First one is flexibility. FPGAs allow designers to make changes to the design even after implementation, providing great flexibility during the prototyping phase. The second one is rapid development. Unlike ASICs, which require weeks or months to fabricate, FPGAs can be programmed and reprogrammed quickly, making them ideal for fast iteration and testing. The third one is cost effective. FPGAs are much cheaper than fabricating a customer ASIC specifically for low volume production. This makes them an attractive option for prototyping new design. The fourth point is real world testing. Prototyping with an FPGA enables designers to test their design in real world conditions, which is often more informative than simulation alone. This allows for the detection of timing issues, more consumption problems, and other real world challenges. So there are FPGA tools and development environment. So designing for FPGA requires specialized software tools that allow engineers to write code, synchronize the design, and configure the FPGA. So some popular FPGA development tools include the Vivado, a powerful development suite for Xilinx FPGAs offering tools for simulation, synthesis, and programming. Then there is one Intel Quartus, a development tool for Intel FPGA, formerly Ultra, providing similar functionality for simulation and programming. So in conclusion of this module, we have explored three important aspects of describing and testing VLSI design: describing chip with Verilog, testing design with simulation, and quick prototyping with FPGAs. So Verilog is a powerful language for describing digital circuits, allowing engineers to model design at various levels of abstraction. Simulation enables engineers to test their design virtually, ensuring they work as expected before fabrication. A FPGA provides flexible and cost-effective way to prototype VLSI design and test them in real-world scenarios. Together, these tools and techniques form a crucial part of the VLSI design process, allowing engineers to efficiently design, test, and prototype complex digital systems. Whether you are describing a simple logic gate or a full-scale processor, mastering these methods is essential for success in VLSI design. So in the next module, we will learn about the chips. So in the world of VLSI design, once the digital logic of the chip is defined and the high level design is completed, the next step is to bring the design to life physically. So the phase involves physical design, chip testing, and the software tools are used to facilitate this complex process. So in this module, we will cover these three key aspects Okay, the physical design, the chip design or chip testing, and the software tools used for the trade. So what is physical design? Physical design is the process of converting a logical representation of a circuit, usually created using hardware descriptions languages like Verilog, into a physical layout that can be fabricated on a silicon wafer. So it involves creating the actual arrangement of the components such as transistors, gates, wires, and other circuit elements. So this process ensures that the physical placement of the components on the chip adheres to design rules while meeting performance goals such as speed, power consumption, and area efficiency. So physical design is a critical phase in the VLSI design flow as it directly impacts the chip's functionality and manufacturability. So what are the steps in physical design? The first is floor planning. So the floor planning is the first step in physical design where the designer decides the general layout of the chip, such as where different functional blocks will be placed. The floor plan defines the chip's overall size and organize the major components to minimize the distance between related components, reducing power consumption and improving performance. The second is placement. After the floor plan is defined, the next step is placement. In placement, individual components like standard cells means transistors and the logic gates are placed within the defined floor plan. So the goal is to minimize wire length while avoiding overlaps and ensuring there is enough space for routing. So the placement process affects not only the speed and the power of this circuit, but also the manufacturability of the chip. Third is routing. Once the components are placed, the next step is routing. Routing is the process of connecting the components with wires, creating the interconnections that allow signals to flow between the components. So the routing process must account for factors like signals integrity, crosstalk, and delays. The fourth one is clock tree synthesis. In complex design, clock signals are used to synchronize operations across the chip. So clock tree synthesis (CTS) is the process of designing and distributing the clock signals to all parts of the chip in such a way that it reaches each component at the correct time. Proper CTS ensures that the chip operates at the desired clock speed while minimizing clock skew, which can lead to timing errors. Then comes the design rule checking. So design rule checking is the process of verifying that the physical layout complies with the manufacturing rules of the foundry that will produce the chip. These rules ensures that the layout is manufacturable and that there are no issues that could cause defects during fabrication such as improperly spaced layers or wires. Then comes layout versus schematic. So after completing the placement and routing steps, the final physical layout must be checked against the original semantic check to ensure that the design is correct and consistent. This process, known as LVS, compares the logical representation of the design with the physical layout to ensure that no mistakes were made during the physical design phase. Then comes power and timing analysis. So the power and timing analysis checks ensures that the chip meets performance goals like timing closure, power consumption, like these. So the designer uses static timing analysis (STA) tools to check for timing violations and optimize the design. So after understanding the steps in physical design, so there are some key challenges in physical design as well. The first one is timing closure. Achieving timing closures means ensuring that every data path in the circuit meets setup and hold time requirements. So data arrives reliably within each clock cycle. This requires adjusting cell sizes, placements, and routing, and often involves iterative optimization using static timing analysis tools to eliminate timing violations without degrading other design metrics. Then comes the clock distribution. A critical challenge in synchronized design is the clock distribution, which involves building a well-balanced and low-skew clock tree that delivers the clock signals to all sequential elements, like flip-flops, simultaneously. Skew or delay mismatches can cause incorrect data capture, so techniques like H-tree structure, clock gating, and buffer insertion are used to optimize timing and the power. Then comes signal integrity. Maintaining signal integrity means preventing unwanted disturbance like crosstalks, reflection, or glitches that can corrupt data. So this requires careful routing, shielding critical nets, spacing signal lines properly, and managing load, capacitance, and drive strength to preserve signal quality. Then comes power consumption. Power efficiently is crucial. So especially in battery powered or heat sensitive devices, dynamic power and static power must be minimized through smart cell placement, use of low power batteries or libraries, power getting multi-voltage domains, and the clock getting strategies during the design. Then comes thermal management. As power density increases, heat concentration can cause thermal hotspots that affect performance and long-term reliability. So I repeat, so designer must plan for effective thermal distribution through floor planning, heat-aware placement, and spreading high-power components apart. Then comes area optimization. With the demand for more functionality, smaller form factors, physical designers must minimize chip area without violating design rules. So now let's move forward and see what is chip testing. So chip testing is the process of verifying that the fabricated chip works as expected and meets all the specified requirements. After the chip has been physically manufactured, it undergoes extensive testing to detect any defects, manufacturing errors, or performance issues. So testing ensures that the chip performs reliably under real-world conditions. So testing is essential to guarantee that the chip will function as intended in various electronic systems. It helps identifying issues like timing errors, electrical failures, and logical problems that could affect the chip's functionality. So what are the types of chips testing? The first one is functional testing. It checks if the chip gives correct output for given input or not. Then comes the parametric testing. It measures electronic or electrical parameters to meet design specifications. Then comes boundary scan testing. It tests pin level connections using scan chains. Then comes built-in self-test. Enables the chip to test itself internally. Then comes delay and timing testing. Verifies signal timing meets speed requirements. Then comes stress testing. It tests chip reliability under the extreme conditions. Then comes the regression testing, which ensures updates and allow you to don't break existing functions. So after understanding types of chip testing, now let's see some challenges in chip testing. The first one is high testing cost. So chips testing is a resource intensive process that requires specialized equipment, skilled engineers, and significant computational resources. As chip complexity increases with the billions of transistors and the multiple cores, the cost of development and running thorough test cases grow substantially. Then comes limited test coverage. Ensuring full test coverage, meaning every possible fault or failure is tested, is extremely difficult in modern VLSI design. Complex logic, multiple functional modes, and deep signal path make it challenging to simulate and test all corner cases. Then comes speed and efficiency. In high volume chip production, testing must be both fast and efficient to keep up with demand. So long or overly detailed tests can slow down manufacturing lines. Then comes fault detection difficulty. Some faults are intermittent, rare, or only appear under specific conditions, making them difficult to detect. Then comes power and thermal issues. Certain test scenarios, especially those that exercise many transistors simultaneously, can cause abnormal spikes in power consumption and heat generation. Then come post-silicon debugging. After the chip is fabricated, debugging any functional or performance issues becomes significantly more difficult due to limited observability and controllability of internal nodes. So now let's see some software tools used in VLSI design. So in VLSI design, software tools may play a pivotal role in automating the design, testing, and the verification process. So these tools help streamline the complex tasks involved in designing chips, checking for design errors, and ensuring that the physical layout can be fabricated successfully. So there are some most commonly used software tools in VLSI design and categorized into some following types, like the CAD tools. CAD tools are used for designing and laying out integrated circuits. They allow designers to create semantics, perform simulation, and create physical layouts for the chip. So examples are Cadence, Synopsys, and Mentor Graphics. Then comes the simulation tools. Simulation tools allow designers to test and verify their designs before fabrication. These tools provide virtual environments in which designers can test functionality and performance of their circuits, detect errors, and optimize design. Examples are ModelSim, Vivado, Cadence. Then comes synthesis tools. Synthesis tools convert high-level design descriptions into gate-level representation. So this is a critical step before physical design can begin, as it prepares the design for implementation in hardware. Examples are Synopsys Design Compiler and the Cadence genus. Then comes place and route tools. These tools help automate the placement and routing of components in the physical design phase. They ensure that components are optimally placed on the chip and that all connections are properly routed to minimize delays and power consumption. Examples are Cadence Invoice and Synopsys IC Compiler. Then comes timing analysis tool. Timing analysis tools are used to verify that the chip meets the required timing constant. They analyze the signal delays and ensure that the chip operates at the desired clock frequency without the errors. Examples are Prime Time by Synopsys, Tempest by Cadence. So in conclusion, in this module, we have explored the essential aspect of chip design, including physical design and the chip testing and the tools of the trade used in the VLSI design process. So physical design involves arranging components, placing them and routing them to create a functionally chip layout. So congratulations on completing the VLSI design course. You have taken a big step in leveraging design to enhance your chip making process. So now it's time to put your learning into action. Try integrating these VLSI design concept into your workflows and experiment with design to optimize your project efficiency.
Welcome to today's video on skills required to become an embedded developer. Today, I'm going to walk you step by step through what an embedded developer does and most importantly, what skills you need to learn if you want to become an embedded developer. So guys, by the end of the video, you will have a clear roadmap you can follow to get started. So first, let us understand what are embedded systems and who are embedded developers. Embedded systems are basically small computers built into other devices to do specific tasks. For example, like a microchip inside your washing machine that controls the cycle. Or the best example could be the system in your car that manages the engine or airbags. These devices are called embedded because the computing part is hidden inside them. So, an embedded developer is a person who writes the software that makes these devices and do their jobs correctly. You can think of it like, suppose, if you build apps for phones, you become a mobile developer. If you are building websites, you become a web developer. If you build code that runs inside machines and devices, you are an embedded developer. Now let us try to understand the core skills required to become an embedded developer. So first one, you need to have a solid understanding of C, C++, and peripheral programming. Then you should be aware about embedded Linux or RTOS. Then you should be aware about assembly language, microcontroller, and microprocessor. And finally, you should also have a very solid understanding about digital electronics and datasheet reading. Now, let's move ahead and discuss what is the exact roadmap to become an embedded developer. So you can see, first you need to build foundation, like your C, C++. Then you need to get hands-on with the microcontroller. After that, you need to master hardware and software integration. Moving ahead, you should also study about version control systems like Git, and then you could move ahead for exploring advanced topics. And finally, you should build an amazing portfolio by doing projects, and then you could go for internship. Let us explore each one of them one by one in detailed manner. Now, let us understand what skills you need to build your foundation. So first of all, the most important skill is your C programming. If you want to become an embedded developer, you should absolutely learn the C programming language. Now, you'll be wondering why C? The reason is because C is fast, it gives you precise control over the hardware, and it's been the industry standard for decades. Here's what you should focus on learning C. First of all, pointers. These let you work directly with the memory. Then, learn about bitwise operations. For example, turning individual bits on or off. Then memory management. And finally, memory management, which is very, very much important. Learn how to handle RAM very carefully. Don't feel intimidated. Start with small programs like blinking an LED or printing text to the console. You will build confidence step by step. Now, once you are comfortable with C, it is very much helpful to learn C++. especially if you are going to work on a larger or more complex system where object-oriented programming can make code easier to organize. Finally, having a little bit of assembly language knowledge is also a bonus. Assembly is very low-level code that talks directly to the processor. You don't need to master it, but understanding how it works will help you when you need to optimize performance or troubleshoot tricky bugs. Now, let's move ahead to the next part. So, next part is understanding microcontrollers and hardware. A microcontroller is basically a small computer on a chip. It has processor, memory, and also it has input-output pins so that you can connect to sensors, displays, and other components. As an embedded developer, you will spend a lot of time in writing code that runs on microcontroller. Some popular ones you might start with is like Arduino, very beginner friendly, and it has a lot of tutorials on YouTube. Next one, you could go for Raspberry Pi, which is affordable and powerful. It's also important to learn how to read data sheets. A data sheet is like a big instruction manual for your microcontroller. It tells you everything about how the pins work, what voltage it needs, and how fast it can run, and many more things. So after studying about microcontroller, it's time to move on software and hardware integrations. When I talk about software and hardware integration, it's like working with the RTOs, understanding the peripherals, UART, SPI and I2C protocols, and also understand the debugging tools. Consider this. When your embedded device needs to do multiple things at the same time. For example, like reading sensors, updating the screen, and sending data. It often uses something called real-time operating system. So, with the help of you can create tasks that run parallel, schedule those tasks, they don't interfere, use queues to communicate between tasks safely. Some of the popular RTOs available are like free RTOs, which is open source and very common. So learning RTOs will make you much more employable because many commercial products rely on them to keep everything running smoothly. Then you need to understand the communication protocols. You will need to learn communication protocols like UART, which is a simple serial communication. Think of it like a conversation over two wires. Then there is SPI, which is like a fast data transfer, good for displays and memory chips. Then you have I2C protocol, which is great for connecting multiple devices with just few wires. Don't worry, each of these has a plenty of tutorials on YouTube, and also you could go for these courses. So guys, practice plenty of examples to get hands-on with these things. Finally, if I talk about debugging tools, you can consider a scenario such that your code doesn't just run on the screen. It is also controlling the real hardware. What if things go wrong? So that's why you need debugging tools. You can go for JTAG and SWT debuggers. These tools let you step through your code line by line when it runs on the chips. Or you could go for oscilloscopes. These will let you see electrical signals in real time. So learning how to debug effectively is one of the most valuable skills you can develop. Using these tools will make your life much more easier. Now let's move ahead and try to understand about version control and build system. Just like in other software jobs, you will need to track your code and work with teammates. That's why it's important to learn Git, which is a version control system. With Git, you can keep a history of all changes, work on features in separate branches, merge everything together safely. Many companies will expect you to know this, so practice using Git as soon as you start doing projects. Then, you need to understand the build system, which is very much important. And finally, practice code documentation. Now, let's move ahead and try to understand what are the advanced topics you need to keep learning. Now, once you have got the basics down like C programming, microcontroller fundamentals, and debugging, there are some advanced topics you can start exploring to really level up your skills. Let's first talk about embedded Linux. Sometimes you will work on devices powerful enough to run on Linux. This is common in things like routers, industrial controllers, or advanced IoT devices. Learning embedded Linux involves like how to configure and build the Linux kernel, working with device drivers, and many more things. Next up, you have bootloaders and memory management. A bootloader is like a small program that runs when a device powers on.
It initializes the hardware and loads your main application code. You will learn how bootloaders work, how firmware's update happen, and how to keep the system secure. Next up, you have power management. Especially in battery powered devices, you will need to know how to reduce power consumption. This means learning to put microcontrollers into sleep mode, wake up, interrupts, optimize performance without wasting energy. Then you could go with little bit knowledge about security basics, like as more devices connect to the internet, so security is a big concern all over there. So you could understand about securing boot and firmware verification. Then you could learn about encryption of stored and transmitted data and many more things. So these are some of the advanced topics you can consider exploring more after you have covered your fundamentals. So guys, one of the best ways to learn embedded development is to build real projects. Let's go over some of the ideas that help you get started with. So you can work with LED blinker with button input, which is a simple project where you control an LED with a button press. You will learn the GPIO basics and debouncing techniques. Then similarly, you could make like variable step counter, where you use an accelerometer sensor to count steps and display the count. This is also very basic and amazing project. And finally, you could make a mini drone controller, which is kind of an advanced project. If you want a serious challenge, build a basic controller for a small drone, including motor control and sensor feedback. Now, when you finish the project, document it well. Write it down what you did, share your photos and codes on GitHub, and maybe even make a short video demo. Employers love seeing practical examples of your work. Now let us talk about jobs and internships, because they are a fantastic way to get real-world experience. Here are some of the tips that I'm going to give you to get started. First, start early. Don't wait until you are in your final semester. Many companies have summer internships for second and third year students, so you can rely on that. Next one is build a portfolio. When you apply, show them your GitHub projects, photos of your hardware builds, or even a short video where you explain what you made. This proves you are passionate and proactive. Network and reach out. Sometimes internships aren't advertised. Reach out to companies by email, connect on LinkedIn, or attend local tech meetups. Then target the right companies. Look for organizations that work on IoT products, automotive electronics, consumer electronics, or industrial control system. Even small companies or startup can give you amazing hands-on experience. And always be ready to learn. During your internship, you might not understand everything right away. That's very much normal. Take notes, ask questions, and soak up as much as you can. And finally, go for certifications and online courses. If you can take online courses to strengthen your resume, it is going to add up a lot of benefit. And finally, keep on learning, because embedded systems keep on evolving.
Hello, welcome back guys to Embedded Systems course. So have you ever used a microwave, smartwatch, or even a car with automatic headlights? Then you have already interacted with embedded systems, the hidden technology driving most of today's smart devices. So in this module, we will introduce you to the world of embedded systems, what they are, where they are used, and why they so matter. So let us get into the agenda first. So here's what we will cover in the lesson. First, we will define the embedded system. Then we will explore its components and look at everyday examples. After that, we will compare the embedded systems with the general purpose computers. Then finally, we will understand why embedded systems are so important, especially in industries like healthcare, automobiles, and IoT. So let's go. First, we'll see what is an embedded system. So it's a computer, but not the kind you use for browsing the internet or editing documents. So an embedded system is a special purpose computer built to perform one or a few specific tasks. It's usually part of a larger machine or device. For example, your microwave has a tiny computer inside that controls the timer, the power levels, the turnable, and that's an embedded system. Think of a general purpose computer like a Swiss Army knife. It can do many things at once. So now think of an embedded system as a precision screwdriver. It's designed to do only one job, but do it extremely well. It doesn't need to open web pages or play music. It just has to get its job done, reliably and efficiently. Now let us see the components of an embedded system. So first, there is the microcontroller or the microprocessor. This is the brain of the embedded system. Then there's memory used to store the software and data. Then input devices like sensors, buttons or switches allow the system to detect the environment or use commands. Output devices like motors, buzzers or displays perform the action, and finally there's a software often called as firmware which runs the logic. So all of this is typically packed into a small circuit board. So let us now move on to the types of embedded system. So embedded systems comes in different forms based on the complexity. The first one is the small scale system are found in the TV remotes or the calculators. Then we have medium scale systems exist in washing machines or TV cameras. Then we have complex embedded systems power things like aircraft, medical devices and smart cars. Their size may vary, but their core purpose is the same: dedicated and efficient control. Now let us move on to see some examples of daily life. So embedded systems are all around you. In your home, your refrigerator, smart TV, washing machine and microwave all have embedded controllers. In healthcare, devices like ECG monitors, insulin pumps and even hearing aids are powered by embedded system. In cars, systems like anti-lock braking, airbags and infotainment are also embedded control. In factories, embedded systems manage robotic arms and assembly lines. And finally, in communication, for the routers, satellites, and even your mobile phone's internet controls rely on embedded technology. Now, let us move on to see some real-world use cases. So let's take a simple example, a washing machine. You select a program and press start. And then what happens next? The embedded system checks the water level, controls the valve, sets the speed, and hits the water and runs the washing cycle. So all of that is handled by a pre-programmed controller without you doing anything else. Now, let us see embedded system versus computers. So what is the actual difference? So here is the one. Embedded systems are designed for a specific task, whereas the regular computers are built for general purpose tasks. So embedded systems are limited in terms of flexibility to one thing pretty well. And in the case of regular computers, they are very flexible and can run multiple applications. Embedded system often lacks a screen or a keyboard, but a regular computer typically has a screen, keyboard, and a mouse. Then embedded system uses less power. And here in the regular computers, it requires more power for general tasks. So embedded systems are limited, I repeat, embedded are very limited memory and usually programmed once, whereas regular computers are large memory and regularly updated or programmed. Now, let us move on to why embedded systems matter. For starters, they enable automation from start fans, I repeat. So for this, enable automation from smarter fans that adjust speed automatically to irrigation systems that water plants only when the soil is dry. Also cost effective, you don't need a full-fledged computer for simple tasks. They are very reliable, built to run for years without failure. Most importantly, they enable real-time processing like deploying airbags in a fraction of a second during a crash. And with the rise of IoT, they are becoming even more critical. So let us now get to see what are embedded systems in IoT. The Internet of Things refers to a network of interconnected devices that communicate and share data to create smarter systems. At the core of the smarter devices are embedded systems which enable them to perform specific tasks, process data, and interact with each other. So, how embedded systems power IoT? The first one is data collection. Embedded systems in IoT devices collect real-time data through sensors to monitor conditions and gather information. Then we have decision making. These systems analyze the collected data, make decisions based on preset rules or algorithms, and take actions such as turning on a light or adjusting a thermostat. Then we have communication. Embedded systems allow IoT devices to communicate with each other, cloud platforms. So this connectivity enables devices to share data, receive updates, or send commands. Then we have energy efficiency. Since embedded systems are designed for specific tasks, they are highly optimized for the power efficiency, ensuring that IoT devices can run for longer periods without draining much energy. Now, let us move on and see why we should consider a carrier in embedded systems. So the first one we have is software and hardware integration. So there are exciting and versatile fields combining both. Then there is a very high demand for embedded system as a carrier. So opportunities in automotive, telecom, consumer electronics, robotics, and IoT. Then we have real world impact. So develop the techs like the smart devices and medical equipment. Then we have innovation. It is ideal for those who enjoy creating practical solutions. Then we have versatile skill set, which is expertise in both software and hardware. Then we have growing opportunities, the strong career prospects with IoT and automation. Then we have diverse roles, so positions in product development, system design, and firmware. Then we have job security. It is a long-term demand in emerging technologies. So in short, if you love solving real-world tech problems, embedded systems offer a dynamic and promising career. So then we have high demand. In industries like IoT, automotive, and robotics, with companies like Honeywell, Google, and Qualcomm hiring engineers. Then the salary range we have is 1.3 LPA to 18 LPA as an entry-level engineer. Then for 5 LPA to 12 LPA as a mid-level engineer, and finally 25 LPA to 40 LPA in the senior roles. And then we have real-world impact, that is a combined software and hardware to develop the innovative technologies like IoT devices and self-driving cars. Then we have a growing career path. So with strong demand and evolving technologies, embedded systems offer a rewarding and a dynamic career. So let's have a quick recap of this. So embedded systems are computers designed for specific tasks. They are everywhere in your home, car, hospital, and even in your pocket. They are different from computers. They are simpler, cheaper, and more focused. They are critical for automation, safety, and IoT. And they are only going to become more important in the future. So let's now move on to the next module. Welcome back to our Embedded Systems course. In the last module, we explored what embedded systems are and how they're part of our everyday devices. But designing and building embedded systems comes with its own set of challenges. So in this module, we will explore the 3 biggest categories of challenges in embedded system development. So before proceeding, let's see what we are going to cover in detail. The first one is limited resources. We'll understand the challenges with the memory, power, and storage in embedded devices. Then we will move on to the real-time requirements, that is why timing is critical in embedded applications and how missing a deadline can be dangerous. Then we have the reliability and safety. So why these systems must be ultra reliable and how international safety standards help ensure that. So let's begin with the first challenge, that is the limited resources. Unlike your phone or laptop, embedded systems are built to do more with less. So most embedded devices are small, affordable, and highly specialized. To achieve this, they are built with very limited resources. This includes very less RAM. Then we have tiny storage space, that is for ROM or flash. Then we have minimal processing power, and then finally we have limited battery or energy source. Now why it is like that? Because they must be cheap, compact, and energy efficient. So let's now move on to see the first challenge for the power consumption and battery life. So most embedded systems are used in the battery powered devices like smartwatches, fitness bands, then we have remote controls and wireless sensors. So these systems need to last for weeks or months on tiny batteries. So developers face two major power challenges. The first one is minimize power usage. The system must consume as little power as possible, especially when idle. That's why low power models like sleep or dead sleep are used. Then we have optimize the processing time. The faster the processor finishes a task, the sooner it can go back to sleep, saving energy. So in short, embedded systems must be smart about energy use. Every milliampere matters. Then we have the second challenge, that is limited RAM memory. So RAM is a temporary memory that stores data while the system is running. In embedded systems, RAM is extremely limited, sometimes just 2 kilobyte or 8 kilobyte. So compare that to your phone, which may have 8 GB of RAM, a million times more. So with so little memory, developers must avoid the unnecessary variables. Then they must use lightweight code. Then they should avoid memory leaks or inefficient loops. One small error in RAM usage can crash the entire system. So memory management is a key skill in embedded programming. Let's now move on to the third challenge. Limited ROM or flash storage. Or flash memory is where the embedded system software or firmware is stored. The memory is also very limited, sometimes 32 kilobyte or 128 kilobyte. So developers must compact optimized code. They should avoid large libraries or unused features. They should use the efficient data storage techniques. So there's no space for bloated programs or unnecessary functions. Every matters. That's why most embedded systems are written in or assembly, because these languages gives developers full control over how memory is used. So let's now move on to the fourth challenge, that is the processing power limitations. So embedded systems don't have powerful CPUs like laptops. So many use bit or 32-bit microcontrollers, which are very limited processing capability. This means you can't run heavy tasks like video processing or AI models unless the system is designed for it. The code must be lightweight, fast, and focused. So the challenge is to build efficient logic that solves the problem with minimum resources. Then we have real-time requirements. What does it mean? So in many embedded systems, it's not enough to just get the job done. It must be done on time. A real system is one where tasks must be completed within a fixed time limit. For example, an airbag must inflate within milliseconds of a crash. A medical monitor must show real-time heart activity. If the task is delayed even by a second, the system may fail its purpose. Then we'll see why timing is crucial. So real-time performance is critical in many industries. The first one is automotive. For systems like ABS or lane, timing is everything. Then medical devices like pacemakers or ventilators must work in real time. Then we have aerospace. Any delay in control system can be life. So in such systems, the challenge is to guarantee the response time, no matter what. So this means optimizing not just the code, but also the hardware and operating system. Then we have types of the real-time systems. So there are basically two types of real systems. The first one is hard real-time. Under this, these systems must never miss a deadline if that serious failure or danger can occur. For example, airbags, pacemakers, industrial robots. The second one is soft real-time. Occasional delays are tolerable, but performance may drop. Examples like video streaming, voice recognition. In soft real-time systems, a short delay is okay. In real, there is no room for error. Then let us understand the reliability, why it matters. So embedded systems often need to run for years without crashing. You don't want your washing machine or ATM to fail randomly. So in critical systems, failure can be dangerous. Imagine a ventilator suddenly restarting or a robot arm going out of control. So embedded systems must be tested under all conditions including temperature, humidity, vibration and long operation. They must recover from errors, handle powerful failures and log issues for the diagnostics. So let us now move on to understand the safety in embedded systems. So safety is about preventing harm to people, property or the environment. So embedded systems in cars, trains, airplanes and hospitals must follow the strict rules. So safety is ensured through the redundant systems, that is the backup hardware or logic. So then we have watchdog timers to restart the system on hang. Then we have emergency shutdowns. So testing for safety is not optional. It's required by international laws. Then we have the global safety standards. So these are the global standards that every safety critical embedded system must follow. The first one is IA6262 for the automotive electronics. Then we have IEC 61508 for industrial systems. Then we have DO178C for the avionics software aircraft. Then we have IEC 62304 for the medical software. So these standards ensure that the system is designed, tested and verified before it's used in the real world. For developers, this means writing cleaner code, testing rigorously and documenting everything. So let's now have a recap of what we have learned. So let's quickly summarize. The first one is limited resources mean developers must write efficient, optimized code. Then we have real-time requirements mean tasks must be completed within strict time limits. Then we have reliability and safety are non-negotiable. In critical systems, failure can lead to danger. So overcoming these challenges is what makes embedded systems both complex and exciting. So let's move on to the next module. Welcome to the chapter 3 of our embedded systems course. So in this session, we'll talk about the brains of embedded systems, the microcontrollers and the processors. So here's what we will learn in this module. We'll first see what is a microcontroller. Then we will see the difference between a microcontroller and a microprocessor. Then why microcontrollers are important in embedded systems, and then we'll see what is a processor cycle, and then finally we'll see the role of the processor in a microcontroller. So let's get started. So let's move on to understand what is a microcontroller. A microcontroller is a small computer on a single chip. It contains there is a central processing unit. Then it contains RAM, there is a random access memory, the temporary memory. Then we have ROM or flash, that is for the storage, that is a read-only memory. Then we have input or output ports, and even sometimes we have timers, ADCs and communication interfaces. So all of this is packed into a single integrated circuit, often smaller than a coin. So in simple words, a microcontroller is like a tiny brain that can take input, process it and give the output all by itself. So let's move on and see the real life analogy. Think of a microcontroller as a self-contained robot that is basically a simple computer on a single chip. It has eyes and ears, that is sensors as input. It has a brain, that is a CPU for processing. Then it has voice, that is the output. So everything is built in. It doesn't need the external components to function. That's why microcontrollers are perfect for the embedded systems that do one job very efficiently. So let's now see the difference between a microcontroller and a microprocessor. So, in terms of purpose, a microcontroller does a specific task and a microprocessor does the general purpose computing. So microcontroller has CPU plus RAM plus input-output devices, and a microprocessor only has CPU. The cost for a microcontroller is very less, and for a microprocessor it is higher. The power consumption of a microcontroller is very low, and a microprocessor it is very high. The size of a microcontroller is very compact, and the microprocessor is larger, needs more chips. Then microcontroller is used in the embedded systems and the microprocessor is used in the computers and the laptops. So a microcontroller is like a compact toolkit with everything inside, and a microprocessor is like a CPU that needs the external ROM and the input-output devices to work. So let's now move on to see the visual explanation. So imagine building a radio. With microprocessor, you buy separate components like processor, memory, storage, ports, and wire them together. So with a microcontroller, everything is already in one chip. You just program it and use it. So that's why microcontrollers are simpler and more suited for the embedded systems. So now let's move on and see the importance of microcontrollers in system. So embedded systems often need to run a specific task, be compact and affordable, use very little power, run for years without an error. And microcontrollers are perfect for this because they have low cost, can be battery operated, come with all the components already built in, and they are reliable and easy to program. So that's why you will find microcontrollers in everything from washing machines to drones to heart rate monitors. Let's now see the common microcontroller applications. So here are just a few examples of when microcontrollers are used. The first one is microwave, that is the controls timing, heating and display. Then we have car, it manages airbag, sensors and auto wipers. Then we have camera that adjusts the focus and shutter automatically. Then we have Bluetooth earphones, it handles the audio and the battery. Then we have the smart light that receives input from application and changes brightness. So in each of these, the microcontroller runs a single focus based on the user input or sensor feedback. Let's now move on and see what is a processor cycle. So let's now understand how a processor inside a microcontroller actually works. So every controller runs in a loop called the processor cycle, which includes three main steps. The first one is fetch, that is get the instruction from the memory. Then we have decode, that is understanding what the instruction is. Then we have execute, that is to perform the action. So this loop happens millions of times per second, allowing the controller to read the input, process data, and control the output in real time. So the real world analogy, we have the processor cycle. Then we have the role of the processor in microcontroller. The processor is the core decision maker in a microcontroller. It does things like reads data from the sensors, that is for example temperature. Then it compares the values or runs calculations. Then it sends signals to the motors, displays or alarms. And then it stores the important data or settings in memory. Think of it like the brain of the system, deciding what to do, when to do it, and how to react to the environment. So let's now move on to see the processor having complete control. But the processor alone is not enough. It works with the peripherals like ADC. So then let's move on to see the processor plus peripherals is equal to complete control. But the processor alone is not enough. It works with the peripherals like ADC. It works with ADC, that is analog to digital converter. Then we have timers, and then finally we have serial ports like UART, SPI and I2C. These peripherals help the processor interact with the real world to read voltage, measure time, or send data to other devices. That's what makes a microcontroller such a complete and powerful solution in embedded systems. So we have certain key takeaways. So let's recap what we have learned. A microcontroller is a mini computer with a CPU, memory, and input-output in one chip. A microprocessor is just the CPU. It needs external components. Then we have microcontrollers are perfect for embedded systems as it is compact, cheap, and low power. The processor cycle includes fetch, decode, and execute. The processor is the brain, but it works with the peripherals to control the device. So microcontrollers are all around us. They make our devices smart, efficient, and interactive. So by understanding how they work, you are opening the door to a whole world of innovation, electronics, and automation. See you in the next module. Hello and welcome back to the module 4 of our Embedded Systems course. In the last few modules, we explored the components that bring embedded systems to life. But today we were diving into the core of the system, the processor itself. More specifically, two major architectural structures that shape how processors work. So, first we will see CISC, that is the Complex Instruction Set Computer, and then we will get to know about RISC, that is the Reduced Instruction Set Computer. By the end of this module, you will know what makes these architectures different, where they are used, and how to choose the right one for your project. So, let us now move on and see what is CISC. CISC stands for Complex Instruction Set Computer. It is a type of computer processor architecture that is designed to complete tasks with fewer lines of assembly code by using the complex and the multi-step instructions. This reduces the number of instructions needed to write a program, which was super helpful back in the days when memory was limited and expensive. Most instructions in CISC are variable in length and complexity. The hardware must be smart enough to decode and execute them, even if they involve multiple steps internally. Then we have advantages of CISC. So what makes CISC useful in embedded systems? First, it allows the compact code. Because each instruction does more, programs can be smaller, which saves memory. Second, it has a built-in complex operation, so you don't need to manually code every step. Third, the CISC processors often have strong backward compatibility. Your old code still works. That's especially useful in the industry and legacy systems. Then let's understand these advantages of CISC. It's not perfect. The hardware is more complex, which means higher power consumption and more heat. Downside for battery-powered devices. Instructions take longer to decode and execute, making it harder to design high-speed pipelined processors. Because instructions vary in size, timing is inconsistent, which is not ideal for real-time systems. Then we have examples of CISC in action. So where do we see CISC? The most popular CISC architecture is x86, used in Intel and AMD processors for the PCs and industry controllers. Embedded system, the 8051 microcontroller, a CISC-based chip, is still used in washing machines, medical devices, and automotive electronics. It's not flashy, but it's reliable and cost-effective. Then let us see what RI is like, having a set of simple, fast tools instead of one complicated multi-tool. Each instruction does only one thing, but it does it quickly, usually in one clock cycle. The idea is keep instructions short, predictable, and uniform, which makes it easier to build fast and efficient pipelines. You might need more instructions to get a job done, but each one is lightning fast. So let's now see the advantages of RISC. Fixed length instructions can be pipelined easily, speeding up the performance. Power efficient, which makes it ideal for battery powered devices like and sensors. And it's hardware friendly. RISC processors are simpler to design and scale across performance levels. That's why RISC dominates in mobile, IoT, and the real-time embedded systems. Then let's understand the disadvantages of RISC programs can be larger since complex operations are broken into simpler steps. They also depend heavily on good compiler optimization. So if your compiler is not great, performance may suffer. And finally, RISC uses separate instructions for loading and storing data, which can increase the memory traffic. So let us now move on to the examples of RISC in action. So it is everywhere. The ARM Cortex-M and A series power your smartphones, smartwatches, and even the Raspberry Pi boards. The open source architecture is gaining traction in drones and low-cost IoT chips. So even routers and set-top boxes still use MIPS, a classic RISC architecture. So let's now move on and see the versus RISC, the face-off. So let's compare the two side. So CISC in terms of instruction style is very complex compared to RISC. Then CISC in terms of execution speed is slower per instruction and RISC is faster per instruction. The code size for is smaller, but the code size for RISC is larger. The power efficiency in CISC is lower. The power efficiency in RISC is higher. The hardware cost of CISC is higher and the RISC is lower. So CISC is ideal for legacy industrial systems. RISC is basically made for IoT, the real-time and mobile. So after we have a knowledge of this difference, let us see the use cases of embedded systems. There are some real-world scenarios. An industrial controller running legacy code might use a CISC-based Intel X board. A smartwatch would almost always use RISC-based ARM Cortex-M processor. A drone doing real-time navigation and object detection, likely powered by for its speed and customization. So every system has its own priorities: the power, performance, and compatibility. So the next question arrives: how to choose the right one? So here's a quick checklist to help you choose. If you want a longer battery life, choose RISC. If you need to run the old software, choose CISC. Building a real-time controller, then use RISC. If your building a memory is super limited, then use CISC. If you want free and flexible architecture, there's no right or wrong. It's all about what your system needs the most. So let's now have a quick takeaway. Let's summarize what we have learned. So CISC is the compact code, complex hardware for legacy. RISC is simple, fast, power efficient for embedded and IoT. Both have their strengths and the choice depends on your application's goals. You now have the knowledge to make an informed architectural decision for your next embedded system. So let's now move on to the final module. So in this last module, we will uncover one of the most critical yet often overlooked, the pillars of embedded system, that is a memory. So here's what we will explore. We will first see the difference between the volatile and the non-volatile memory. Then we will see the various types of memory used in the embedded systems. Then we have memory architecture styles like the von Neumann and Harvard. Then we have real-world implementation techniques that boost performance and efficiency. And then we have smart memory management strategies for embedded environments. By the end of this module, you will know exactly how embedded devices store, access, and manage the data they need to function reliably. So even with the tight constraints on power, space, and processing power. So let's now move on and see the foundation of everything, that is a volatile versus non-volatile memory. Let's start simple. Volatile memory like RAM is fast and temporary. Volatile memory like RAM is fast and temporary. It forgets everything when the power goes out. Non-volatile memory like the ROM and flash is just the opposite. It's slower but remembers everything even when powered off. Think of it like your brain. RAM is like your short-term memory where you store today's to-do list. Then we have ROM, that is a flash, is your long-term memory where you have stored your name, your birthday and how to ride a bike. This difference is at the core of how embedded systems make decisions, store instructions and hold on to essential data. So this difference is at the heart of how embedded systems make decisions, store instructions and hold on to essential data. So let's now move on to see the types of embedded system. So let's break down the memory types you will often encounter in the embedded systems and where they are used. The first one is SRAM, that is static RAM. The fast, stable and used for registers and internal caches. It's expensive, so used in the small amounts. Then we have DRAM, that is dynamic RAM. So slower than SRAM but more affordable and denser. You will find it in the applications that need larger RAM. Then we have EEPROM, that is the electrically erasable memory. Good for storing small bits of data like calibration, values or device settings. Then we have NOR flash. It is great for storing code. It allows random access and execution in the place, it is the XIP. Then we have NAND flash, common in the SD cards and USB drives. It is dense and cheap, great for storage but slower for direct execution. So each of this memory type is like a tool in a toolbox. The trick is knowing which one to use when. So let's now see the memory architecture in embedded system. So memory is not just about what you use, it's about how it's organized. There are three main characteristics, I repeat. There are three main architectures you will find. The first one is von Neumann architecture. The code and the data share the same memory and bus. Simpler and flexible but limited by bandwidth. Then we have Harvard architecture. Separate memory and buses for code and data. This allows parallel access, faster and more efficient. Then we have modified Harvard, the hybrid that combines both of, Then we have modified Harvard, a hybrid that combines the best of both the worlds. This is what most modern microcontrollers use. So a von Neumann system is like a single lane road shared by cars and bikes. It can get crowded. And Harvard, the two separate lanes, one for cars and one for bikes. No slowdowns. So let's now move on and see the real world memory implementation. So let's talk about the real applications and the optimizations. The first one is XIP, that is execute in place. So instead of copying firmware into RAM, the MCU runs it directly from flash. It saves the RAM, speeds up the boot time. Then we have shadowing. The critical code is copied from flash so it can run much faster from RAM. Then we have external memory interfaces. So some systems connect to the external PSRAM or flash to expand the memory without adding cost to the chip. Then we have cache and prefetch buffers. So these help bridge the speed gap between memory and processor without the developer doing much. So all these techniques help embedded devices run faster and smarter without needing the massive hardware upgrades. So let's now move on to see the memory management techniques. So finally, let's look at how memory is managed on a day-to-day basis within embedded applications. The first one we have is static memory allocation. So predictable and safe. perfect for the real-time systems where dynamic allocation is risky. Then we have memory pools. So if it is efficient and fast, your pre-allocate blocks and reuse them, avoiding the fragmentation. Then we have DMA, that is direct memory access. So it moves data from memory to peripherals and vice versa without involving the CPU. It is, I repeat, huge power saver. Then we have wear leveling. So it is essential for flash memory, spreads out write or erase cycles to prolong the life of storage. Then we have low power memory modes. So many MCUs let you retain only critical sections of RAM during sleep to save energy. Then we have another one, that is ECC, that is error correction code, especially useful in the automotive and the medical systems where reliability is non-negotiable. So each of these techniques can drastically improve the system's stability, power efficiency, and lifespan. So from the smallest temperature sensor to a complex drone flight controller, memory is the silent hero behind embedded systems. So guys, congratulations on completing your journey into the embedded systems. You know you have a solid understanding of what embedded systems are, how they differ from general computing, and why they're essential in everyday devices. You have explored the key challenges like limited resources, real-time requirements, and the need for reliability. You have learned about microcontrollers, the difference between the CISC and the RISC architectures, and how memory is managed in these systems. With this knowledge, you are well equipped to start building the efficient, intelligent devices. This is just the beginning. Keep exploring, keep innovating, and let your ideas come to life.
Thanks for being a part of this deep dive into the world of IoT, VLSI, and embedded systems. We hope this session gave you a clear understanding of how these technologies are connected and where they can take your career in the coming years. Whether you're exploring smart devices, chip design, or embedded development, the future is full of exciting opportunities. Keep learning, stay curious, and continue building the skills that shape tomorrow's technology.
Staying ahead in your career requires continuous learning and upskilling. Whether you're a student aiming to learn today's top skills or a working professional looking to advance your career, we've got you covered. Explore our impressive catalog of certification programs in cutting-edge domains, including data science, cloud computing, cybersecurity, AI, machine learning, or digital marketing. Designed in collaboration with leading universities and top corporations and delivered by industry experts, choose any of our programs and set yourself on the path to career success. Click the link in the description to know more.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.